Hello, everyone. This is the project for energy management and manufacturing audit. My name is Eduardo Garcia.
I'm Ibrahim Ashraf.
Cesar?
Eduardo Ortiz. So pretty much for the introduction, it's an energy audit of a commercial title manufacturing facility. It evaluates electricity and natural gas usage across production processes. Establishes baseline energy use, operating cost, and CO2 emissions. It uses the utility bills and equipment level logger data for analysis. And then also identifies cost-effective energy efficiency measures without impacting production. Next slide. For the background, pretty much the facility produces decorative tiles, glazed-in bricks, and hand-painted tiles. The total facility area is about 80,000 feet squared, including a 15,000 feet squared of space office. And then it has approximately 140 employees across multiple production areas. And then some of the manufacturing steps includes mixing, milling, shaping, drying, glazing, firing, packaging, and shipping. And then some of the major energy users was compressed air system, ball mills, and natural gas firing kilns.
Right. So now that we have seen how the facility operates, the next step was to establish a baseline for energy use, demand behavior, cost, and emissions. This baseline is what all of our energy efficiency measures are evaluated against. Next slide. So electricity costs are driven by both time of use energy charges and monthly demand charges based on the highest 15-minute load. Natural gas costs are based on the usage, and understanding this rate structure is important because demand reduction and energy savings affect cost differently. So this slide shows the facility's monthly electricity consumption over a full 12-month period. So total annual electricity use is about 409,000 kilowatts hours, and we see higher consumption during the summer and early fall months. So the highest one is in September, and which aligns with the increased production activity. And usage eventually drops during winter months, which shows like the electricity consumption is strongly tied to operational schedules rather than constant base loads. Next. So in these slides, we can see the monthly peak electrical demand, which is measured as the highest 15-minute demand in each billing month. When we sum the monthly peaks of 12 month, the total annual demand came out to be 2264 kilowatt per month. 2264 kilowatt month, and the demand peaks occurs during operating periods and fluctuate month to month, which is important because demand charges are based on the on these peak values rather than the total energy use. Next. So in order to understand load behavior, we classified each 15 minutes interval as operating, which is Monday to Friday, 8 a.m. to 6 p.m. And besides that, everything is non-operating. So operating hours represent normal productions, while non-operating hours mostly reflect the baseline loads like kiln. And demand is significantly higher and more variable during operating hours, which helps identify where controllable loads exist. Thanks. Similarly, a weekday versus weekend comparison shows a similar pattern. Weekday demand is consistently higher due to production activity, while weekend demand is lower and flatter because there's only the baseline load. And this confirms that the most demand spikes are production driven rather than the continuous loads. Next. So using the utility bills, average unit costs were calculated for the electricity, demand, and natural gas. And these values are later used to estimate annual costs and savings for each proposed efficiency measure. So as we can see, the electricity cost turn out to 38 cents per kilowatt hours. The demand cost is $21.65 per kilowatt month, and the natural gas cost is $11.89 per MMBTU. Next. So annual cost and carbon dioxide emission, we can see this uh, table. The annual cost is mostly because of the electricity usage and demand. Those are the large portion of annual costs, while the natural gas dominates emission due to the kiln. This baseline is what we use to quantify both financial and environmental benefits of the recommended measures. Next.
All right. So moving on to the energy efficiency measures, the first one is to reduce the compressor set point. This basically means to reduce the pressure at which the compressor compresses the air and stores it. Essentially, we're recommending to lower it by 5 psi to save on energy. 5 psi is not much of a pressure drop change, so it should not affect manufacturing facilities and processes by much. And this setting the pressure lower will actually save us about $1,100 a year, which is equivalent to 6,000 kilowatts per year of energy. And the nice thing about this measure is that it is very easy to implement, and there are no additional costs that come included with this because all you do is lower the pressure at which the compressor works. So it's very cheap and very easy to do, and it'll save you lots of money in the long run. Moving on to energy efficiency measure number 2. This is to fix compressor leaks. So the compressor is connected to multiple pipes and tubes which carry compressed air. These tubes and pipes tend to sometimes break and start leaking compressed air. And this means that the compressor will start working harder, essentially consuming more energy, which leads to just leaked air, which doesn't do anything, which doesn't provide any benefits to the manufacturing facility. So basically, we're assuming that about 20% of the energy consumed by the compressor results in leaked air. This results in about $4,000 per year of lost energy. So basically, we're proposing to fix all the leaks for all the pipes and the compressors, and we're estimating about a total cost of $2,000. 1,000 comes from capital, and the other 1,000 comes from labor costs. But the nice thing about this is once it is fixed, it will the payback is less than a year. It's about half a year to get that money back from just saving on energy for the compressor by fixing these leaks. Energy efficiency measure number 3 is shutting down the compressor during off hours. Having the compressor on during the off hours doesn't provide much benefit to the facility since there's not much work being done during those times. And having the compressor consume energy during that time is not beneficial. So we're recommending to install a device which automatically shuts off the compressor during off hours and turns it back on during the daytime. So we're estimating about 25% of the energy consumed by the compressor was during the off hours, according to the logger data, which is about 30,000 kilowatts of energy wasted a year and about $11,000 of money gone. So being able to install this, we're estimating about a total cost of $1,000 to install this device in the compressor. So installing this will save us about $11,000 a year. And the simple payback time is about a month. So installing this device will lead to lots of benefits for the energy savings.
So moving on to EEM number 4, the used cog belts for the ball mill. The logger data shows the mill draws power only in short irregular intervals while the electrical panel remains energized with zero load voltage during long idle periods. Fluctuating power draw during operation suggests belt slippage, which is likely caused by the existing V-belt system. Our suggestion is to replace the V-belts with high efficiency cogged belts. This will reduce slippage and improve drive efficiency by about 3%, stabilizing the load and lowering energy waste. The monthly energy use is 1,134.62 kilowatt hours, which translates to 13,615.44 kilowatt hours per year. This indicates measurable annual savings potential from the belt upgrade. As you can see in the table number 4 over here on the right-hand side, total cost savings of this will be 155.22. Our energy savings per year in kilowatt hours would be 408.46. And the implementation cost that we put was around $1,000. For capital 500 and then for labor 500, and our simple payback would be 6.44. Next slide. So moving on to EM5, heat recovery from kilns. Kiln operates continuously 24/7, releasing hot exhaust gas at 180 degrees Celsius with 1 kilogram per second mass flow, indicating a substantial wasted thermal energy. The data shows no shutdowns, meaning heat losses occur even during non-production hours. Our suggestion to solve this is installing a recuperative heat exchanger that can recover waste to wasted heat to preheat combustion air, reducing natural gas use and improving efficiency. The logged energy use is 17,823.61 kilowatt hours per month, which in turn translates to 213,883.4 kilowatt hours per year, highlighting strong potential for cost-effective savings. As you can see over in table number 5, our total cost savings per year will be 5,859. Our energy savings in kilowatt hours per year are around 195,300. And our implementation cost was 50,000. And for capital and labor, it was 25,000. Our simple payback would be 8.53 years. Next slide. And these are some of our references.